Hey folks, welcome to Digimento Education. This is Analog Devices and Circuits Lecture 6. In the last lecture, we ended our discussion with the introduction to half wave rectifiers with the capacitive filter. So let's begin with this lecture and have an intense study on the half wave rectifiers with the capacitive filters. Before that, I like you to please hit the like button if you really like this video, share and subscribe to our channel, and write down your comments below in the comment section. It will be beneficial for us and beneficial for you as well. We will get back to you with your solutions so that it will be more helpful for you guys. Okay, let's begin with this lecture. So we are going to discuss half wave rectifiers with capacitive filter. So let's quickly discuss the concept behind it. So this is again a conventional transformer. This is a diode, and there is a capacitor and a resistor. Capacitor and resistor are connected in parallel. So this is basically a step down transformer where N1 is greater than N2. This is pure AC signal, pure AC supply, and this is VI. Okay, understood? So this is basically, so in this case the capacitor filter is always connected in parallel with resistance RL, and the output voltage VO is basically equal to VC. Okay, so let's plot the waveform. Okay, let's say this is basically VI, this is VM, and this is minus VM. Okay, this is VI. Now let's plot the variation in the output voltage, which is also equal to VC, the voltage across the capacitor. Now since when VI is positive, you can say when VI is positive, your you can say this diode D will be forward biased, so output voltage will be equal to VI. Output voltage will trace VI, will follow VI. So the output voltage variation will be like this. So it's going to be like this up to this particular point. At this point, since the capacitor, you can see after this particular point your VI will become less than VO. Okay, VI will become less than VC. So what would happen, since VI is less than VC, this diode will be reverse biased. So reverse bias, then this will be open circuited, diode will be open circuited, and hence there is no path between your input voltage VI and the capacitor or load resistance RL circuit. Okay, so the capacitor, whatever charge it has gained, it will start discharging through resistance RL. Okay, it will start discharging through resistance RL like this. At this particular point, what would happen, your VI will again be active, and after this particular point your VI becomes greater than the output voltage or the voltage across the capacitor. Since VI is greater than VC, the diode will be forward biased. And VO will again start following VC. VO will start again following your input voltage VI. The same thing will happen here as well. Okay, so this will again follow like this. So this continues, this whole process continues. Okay, so this is the basically extracted DC at the output of the at the output. Okay, so let me just show you. This is equal to VO is equal to VC. You are still getting ripples, and that can be taken care of by using the full wave rectifier that minimizes the ripples, or the regulator, voltage regulator, which is connected at the output of the filter. Okay, so this, let's say this is T1, this is T2, and this is, let's say it is T3. Okay, so this potential, this particular potential is equal to Vm minus Vr. Vr is the ripple voltage. Vr is the ripple voltage. Okay, let's say this particular time period is T discharge. This particular time period is T discharge, and this particular time period is T charge. Okay, this particular time period is T discharge. So okay, and what is this particular time period? This is T naught. Here it is T naught because F naught is basically the fundamental frequency. In the half wave rectifier, we know F naught is the fundamental frequency, fundamental or ripple frequency, as already discussed. Okay, this is how it looks. This is how the output waveform looks. This is since again it basically the ripples basically have the DC plus AC component. This portion is AC, and the shift in the waveform is corresponds to DC present in the circuit. Understood? This is how this should be clear to you. Now let's write some points so that it is more clearer to you. So when diode is forward biased, capacitor charges through diode. Okay, so if diode is ideal, this means that which is short circuited when it is forward bias, then the capacitor voltage Vc follows Vi. Otherwise there will be some potential drop across the forward resistance of the diode that we would have to take care of when we consider the diode to be non-ideal. Okay, so when diode turns off or reverse biased or open circuited, capacitor discharges slowly through a resistance RL. Okay, because discharging time constant is very large, because RLC, which is basically the discharging time constant is very large. This is how it goes. Okay, so there are some cases that you should know, that when T is less than T1 and greater than 0, what would happen? Diode conducts and Vc or Vo follows Vi. Okay, when time T lies between T2 and T1, your capacitor discharges slowly through RL. Okay, and Vc decreases by an amount of Vr between T1 and T2, between this interval diode remains reverse biased. Okay, when time lies between T3 and T2, diode begins to conduct and follows Vi again. So the above process repeats itself. Okay, so now let's basically, so you can see that capacitor discharges and charges in one time period, as it is already clear to us at this point that in the T naught it is both charging and discharging. So with this we can write that T naught is equal to T discharge plus T charge. Okay, and we can approximate it to T discharge because T charge is very small compared to T discharge. Okay, this is important point that I have made here. Okay, so VR represents peak to peak variation in the output. Okay, so this is basically your this thing. So this voltage is VR. Okay, it's a peak to peak variation. Now let's try to find out the peak to peak variation in the output voltage, or you can say it's a ripple voltage. Let's find that out. What is a ripple voltage? Okay, now let's put the heading. Now first one, let's perform the analysis of half wave rectifier with the capacitive filter. So first one is the ripple voltage, VR. Just remember that VR is not the amplitude, it's basically the peak to peak variation in the output. Okay, it's not the amplitude. So ripple voltage, let's try to find that out. Now, so what's happening between T1 and T2? Capacitor discharges or capacitor loses charge. Okay, so the amount of charge lost by the capacitor, can be calculated as, so we can say the amount of charge lost by the capacitor is C into delta V, or you can C into VR, because with this amount, with the ripple voltage amount, so in this case, when between this particular interval, when the capacitor saw a loss of delta Q amount of charge, it also saw a decrease in the voltage by VR amount. It also saw the decrease in its voltage by VR amount. That's why the amount of charge lost is equal to C into delta V, or C into VR. Understood? So when the capacitor basically saw a loss of delta Q charge, and that loss basically corresponds to the loss of delta V amount of voltage across it. Okay, so this should be equal to C into VR, and that loss, that amount, that voltage loss, the change in the voltage loss is equal to VR. The change in the voltage corresponds to VR. Okay, so this is the important thing, delta V, or you can say that delta V is basically the decrease in capacitor voltage in that particular interval. Understood? So what is also happening in this particular interval, in this T1 to T2, when the capacitor is discharging, what is also happening, where the charge is going. So the amount of charge that is basically lost by the capacitor is passed through the resistance RL. So in this case, what amount of current, what amount of charge is flowing through resistance RL? So we can say between T1 and T2 diode remains off. Okay, diode remains off, so no charge flows through the diode, and hence capacitor supplies all the charge to RL, all the charge to RL. So there is only one discharging path, that is through resistance RL. So amount of charge supplied to RL can be calculated as, so that amount of charge supplied to RL can be calculated as average rate of charge flow through RL, which is current through RL, into T discharge. Okay, we can say delta Q is equal to IDC, because the DC is the average current which is flowing through resistance RL in that particular time interval, and T discharge will be equal to T naught, because as we approximated T discharge to T naught. Okay, so delta Q will be equal to IDC into T naught, and both of these expression will be equated. So this is, let's say it is 3, and let's say this is 2, so we can approximate this to 2 should be equal to 3. So we can say that C into VR is equal to IDC into T naught. So we can say VR is equal to IDC into T naught by C, and is also equal to IDC by F naught into C. So we can say ripple voltage is equal to IDC upon F naught C. This is important expression. Okay, so VR, ripple voltage, is equal to IDC upon F naught C. Understood? So peak to peak ripple voltage, you can say it's basically a peak to peak. It's basically peak to peak variation in the output of the half wave rectifier. Okay, so let's now calculate the ripple factor. So what is the ripple factor? You know, the definition of a ripple factor is basically the ratio of RMS value of the pure AC component to the DC component. Okay, so we define a ripple factor. We know that the ripple factor is defined as RMS value of the AC component upon DC component. Okay, now let's have a look at the variation in the output. So we know how does your output look like. So this is how it looks at this, let's say time T1. This is somewhat like this. Okay, so if you keenly observe, the variations are like this. We can approximate the whole variation like this. Although it's like this, but we can approximate to a triangular wave like this. Okay, now in this case we have basically taken an axis which is cutting the ripple voltage, the ripple variations into two halves. Okay, so this is basically your T1, this is T1, and this was your T2, this was your T2, and this is your T3. Okay, this is T1, this is T2, this is T2, and this is T3. So we know that the peak to peak variation corresponds to VR. So this to this variation, this to this variation corresponds to this whole thing is VR, and this is basically equal to VR by 2. This is minus VR by 2, because we have taken this particular axis that cuts the ripple variations into two halves. Okay, this is VR by 2, this thing is VR by 2, this is minus VR by 2. This time is T1, this is T2, and this is T3. So we can say this is basically the AC component of the output. So we can say that RMS value of AC component, which we can represent as Vrms prime, is equal to, now for the triangular wave, what is the RMS value? VR upon 2 root 3. Okay, so okay, this is VR upon 2 root 3. Why 2 root 3? Because we know the amplitude of this triangular pulse is VR by 2, and the amplitude, or you can say that it is equal to Vm dash by root 3, where Vm prime is VR by 2. Okay, that's why it is equal to, so RMS value of the AC component, which is represented by Vrms prime, is equals to VR by 2 root 3. You are not supposed to use the Vrms prime as was given in the half wave rectifier when it was not used, when a capacitive filter was not connected to the output, connected at the output of the half wave rectifier. This is totally different. Okay, you should not get yourself confused with the concepts behind the half wave rectifier without and with the capacitive filter. Okay, otherwise if you mingle up everything, you are basically going to end up with the wrong results. Okay, this should be equal to VR by 2 root 3. This is Vrms prime. Okay, understood? This is really important, so I'm marking it separately as important. Okay, you should basically be well versed, we should be very clear with this. Now we know that Vrms prime is equal to VR by 2 root 3. Now we know what is VR. VR is equal to IDC by F naught C. So IDC by 2 root 3 F naught C. Now what is IDC? We know it is equal to VDC into RL. VDC divided by RL. Sorry, VDC divided by RL, 2 root 3 F naught C. Now what is ripple factor? Ripple factor is RVRMS prime upon VDC, as we already know. So it will be equal to 1 upon 2 root 3 F naught C RL. So your ripple factor comes out to be 2 root 3 F naught C into RL. So ripple factor is equal to 1 by 2 root 3 F naught C RL. This is very important point that has been made here. That's the expression when you encounter a half wave rectifier circuit with the capacitive filter. Okay, so this is highly important. So it will be R is equal to ripple factor is equal to 2 root 3 F naught C RL, and it is very important to observe that R is inversely proportional to load resistance RL. Okay, so if we basically choose very high resistance, very high load resistance, large load resistance, then ripple factor very small, and we shall see very small ripples in the output. We shall see very small ripples at the output. So if RL is large, ripple factor R will be small. Okay, so you should always connect large resistance RL at the load so that we get very small ripples at the output. Okay, so it is a very important point that has been made here. Okay, so smaller case, so we can say that smaller R can be achieved by connecting large resistance RL at the output. Okay, this is very important point that has been made here. Okay, now let's discuss the third point in the analysis part. What is the DC output voltage? We know one DC output voltage should be equal to IDC into RL, but how can we calculate from the graph? Okay, so your this is basically your DC, basically this is basically your VDC. Okay, and this was basically your ripple variation, ripple voltage variation. This is the output variation. Okay, this is T1, this is T2, and this is T3, and so on and so forth. So now if you keenly observe, if you observe it keenly, so we can say this is basically your, this amplitude is basically your Vm. Okay, and this is basically Vm minus Vr, as we already saw when we started our discussion on the half wave rectifier with the capacitive filter. Okay, so this is VDC and this is Vm minus Vr. What is VDC? VDC, if you observe from here, is equal to Vm minus Vr by 2. Is it clear? So your VDC will be equal to the average of the two extremums. So VDC will be equal to Vm plus Vm minus Vr by 2. The 2 Vm minus Vr by 2, it should be equal to Vm minus Vr by 2. And VDC can be written as VDC is equal to Vm minus IDC upon 2 F naught C. Understood? Okay, and we can also approximate this thing to a Thevenin equivalent circuit. So we can say this is V Thevenin and 1 by 2 F naught C. So we can say V Thevenin is equal to Vm and R Thevenin is equal to 1 by 2 F naught C. Okay, so we can approximate this thing to this. Understood? So we can draw the Thevenin equivalent circuit by like this. This is the DC output voltage VDC, and this is V Thevenin, which is equal to Vm, and this is R Thevenin, which is equal to 1 by 2 F naught C, and this is the output voltage which is equal to VDC. Okay, understood? This is how it goes. Now let's discuss another point, another subtopic, the fourth one, which is basically your angle of conduction. Angle of conduction. Angle of conduction basically, when we discussed the half wave rectifiers without your capacitive filter, the angle of conduction that we concluded was equal to 180 minus 2 theta. Okay, it was equal to 180 minus 2 theta. Now, and with theta where your theta was sine inverse of V gamma by Vn, where V gamma is the cut-in voltage. Now basically it's again the definition remains the same. Angle of conduction represents the angle for which your diode conducts. So you can say it is the duration, for which diode conducts. Okay, so let's have a look. Let's try to shift the whole curve by pi by 2 on the left side. Okay, let's try to shift the whole curve by a little bit by a let's basically apply a phase shift of pi by 2 to the curve. So okay, let's say this is how your output waveform looks. This is a pure AC signal. Now okay, this is how, let's say, your input waveform looks. Now we are taking a cosine signal. we just have applied a phase shift of pi by 2, so that our calculations become easy. And now for this now when is the diode charging? When is the diode conducting? When is the diode conducting? Conducting means it is forward biased. Okay, we are considering the diode to be in the conduction state, which basically implies, which tacitly implies the diode is in forward biased. So let's say this time when it is charging, let's say it is at t is equal to minus delta t. Okay, this is at t is equal to minus delta t. Now at this point the capacitor basically charges and follows Vi. The capacitor charges and follows Vi. Okay, it must be discharging before t is equal to minus delta t. Now it is charging up to this particular point, this is 0. Okay, and then again it discharges like this. So we are considering this. Understood? Now for this particular duration, which is t is equal to delta t, it is charging, it is following Vi. So let's say this is Vi. Okay, so we can say that diode conducts in for t is equal to delta t duration. So we can say that diode conducts from t is equal to minus delta t to t is equal to 0. Therefore delta t is the conduction duration. Okay, conduction means, conduction is equivalent to saying it is forward biased. Okay, so during this particular interval, since your Vc is equal to Vo follows Vi, so this can be approximated to, we can say Vc will be equal to, Vo will be equal to Vc is equal to Vm cos omega naught t for this particular interval, only for this particular interval. So at t is equal to minus delta t, what will be your Vo is equal to Vc is equal to Vm minus Vr, because we know this is Vm and this voltage, as I already told you before, is equal to Vm minus Vr. So we can approximate this thing too. So we can say that Vm minus Vr is equal to Vm cos omega naught delta t. Okay, sorry, it is minus delta t, because at t is equal to minus delta t, at t is equal to minus delta t, Vo is equal to Vm by Vr should be equal to Vm cos omega naught minus delta t. So Vm minus Vr is equal to, since cos is an even function, we can say it is cos omega naught delta t. So Vm minus Vr, now we can write this thing here, that we can write it as like this, cos omega naught delta t by 2. Now apply this double angle formula. We can apply, since we know that cos 2 theta is 1 minus 2 sine square theta. So we know that cos 2 theta is 1 minus 2 sine square theta. Okay, since theta as theta is very small, since theta is very small, we can approximate this thing to 1 minus 2 theta square. Okay, we can approximate it to 1 minus 2 theta square. Since delta t is very small, because we already considered before that t charge is very small as compared to t discharge. So t charge is very small as compared to t discharge. So we can say that Vm minus Vr is equal to Vm. Now the cos term will be removed and it will be equated to 1 minus 2 theta square, which is 1 minus 2 omega naught delta t by 2 whole square. Okay, so this can be approximated to this particular expression. So your Vm will cancel, negative sign will cancel. What are we left with is this. So this becomes equal to 2 by 4 omega naught square delta t square. Okay, and Vm will be there. So we can say that Vr is equal to Vm by 2 omega naught delta t whole square. And from here this implies that we can say omega naught delta t is equal to square root of 2 Vr by Vm. This is the conduction angle. Okay, this is in radians. You should remember this thing, that this thing is in radians. So and this is basically the angle of conduction. This is the angle of conduction. Omega naught is in radians per second. T, second will cancel. This is in radians. So let me again write that angle of conduction which is equal to omega naught delta t square root of 2 Vr by Vm. This is very important. Okay, so hopefully it is clearer to you, and I hope that I was credible enough to explain you in a better way about each and every part of the half wave rectifier with the capacitive filter. Okay, so if you have any doubts, please write down your doubts in the comment section. If you're feeling dubious enough to, if you are basically facing any sort of dilemma or difficulty at any point of our discussion that we had, please write that down in the comment section below, so that I can basically so that I can basically help you out with those problems. Okay, in solving those problems. So next point of discussion is average diode current. So when we had a discussion on half wave rectifier without capacitive filter, we saw that average diode current was also equal to the average current flowing across the resistance RL, which was your IDC, and which was equal to Im by pi. Now in this case, since we are using the capacitive filter, we are that's not going to be the same. That's not going to be equal to Im by pi. That's going to be different. There's going to be something different. So please make a note of this thing. Let's represent this thing with ID average. So in the half wave rectifier, when we basically did not connect your capacitive filter at the output, your diode average current was also equal to the average current which was flowing across the resistance RL. But in this case, it won't be the same. It will be different. So if we apply the KCL at that node, so we can say through KCL, Kirchhoff's current law, average diode current is basically the sum of average capacitor current and average load current. Clear? In the previous case, your average diode current was equal to average load current. So we can say that is equal to ID average is equal to IC average plus IDC. Okay, this is what I mean to write. Okay, so now we know everything about your about IDC. Up till now we know everything about IDC. What are the expressions corresponding to it? Now we have to calculate your average capacitor current. So that can be calculated. Your IC average can be calculated by the principle of law of conservation law of conservation of charge. Law of conservation of charge. Charge lost is equal to charge gained. Okay, so we can say it should be equal to charge gained by the capacitor during charging is equal to charge lost by the capacitor during discharging. Charge lost by the capacitor during discharging. Okay, this is the law of conservation of charge. So what is the charge gained by the capacitor during charging? Should be equal to IC average into delta T, because in the delta T interval the capacitor is charging, and during discharging it should be equal to C into VR, because it is discharging, because it is losing the charge corresponding to the decrease in the voltage across it of VR. VR is the amount of decrease in the output voltage of the capacitor during discharging. So it should be equal to IC average into delta T. So average capacitor current into delta T is the time interval in which it is charging. Okay, so IC average is equal to C into VR upon delta T. Understood? Now we know that what is VR? C upon delta T. What is VR? IDC by F naught C. Now what is delta T? What is delta T? Now we know that omega naught delta T is square root of 2 VR by Vm. So delta T will be equal to 1 by omega naught, this thing. So we can say that IC average is equal to C upon square root Vm by 2VR omega naught into IDC by F naught C. Okay, omega naught is 2 pi F naught will cancel, capacitor value will cancel, and on solving you get IC average equal to 2 pi IDC to square root of Vm by 2VR. This is your IC average. Okay, so if you just take 2 inside, it will be equal to 2 Vm by VR. So we can say that IC average is equal to pi IDC square root of 2 Vm by VR. So this is basically your IC average. Now, so if you plug this value in the above expression of ID average, so we know that ID average is equal to IC average plus IDC. So this is equal to pi into IDC square root of 2 Vm by VR plus IDC. This comes out to be IDC into 1 plus pi square root of 2 Vm by VR. So this is basically your ID average. This is very important expression. This is very important expression. Okay, understood? Now, okay folks, I am basically ending this lecture here. Please go through this lecture very carefully and try to understand each and every ounce of this particular lecture. And also please be well versed, make yourself well versed with the concept that I covered in the last 5 lectures, because these lectures are very important, and these questions are frequently asked in the PSUs or PSU, GATE or IES examinations. So please be well versed with that, and if you have any doubt, kindly write those doubts in your comment section below, or hit the like button if you really like this video, subscribe and share this channel to your colleagues and to your friends, okay, so that they can also experience the benefit from us. Thank you very much.